Hi, my name is Tarachan, Assistant Professor in Mechanical Engineering Department, RVR and JC College of Engineering, Guntur. I welcome you all to this session. Today my topic is exergy. So, exergy is the useful work potential of energy. The useful work potential of a system is the amount of energy we extract as useful work. The useful work potential of a system at a specified state is called exergy. Exergy is a property and is associated with the state of the system and the environment. So, the same equivalent word to the exergy is the availability, which was made popularly in the United States by MIT School of Engineering. And exergy was introduced in Europe. Availability or exergy is a work potential and maximum useful work. This work is a function of initial state and final state and process which the system undergoes. So this work always a function of initial, final and process form. So in the availability or exergy analysis, the initial state should have to specify first, and for getting more, that means maximum work output, the process should be executed is reversible. The final state is a dead state. So if the state of the system differs from that of the environment, an opportunity exists for developing work. However, as the system changes state towards that of the environment, the opportunity diminishes, ceasing to zero when the two are in equilibrium with one and another. The system is said to be in the dead state when it is in the thermodynamic equilibrium with the surroundings. The system has zero availability at the dead state. So these are some of the characteristics for the exergy. So first of all, once the environment is specified, the exergy can be viewed as system property, and the value of the exergy cannot be negative. Exergy is not conserved. Irreversibilities destroy exergy, and can also be viewed as minimum theoretical work input required to bring the system from dead state to the given state. So here the dead state, if we're going to uh, discuss exergy analysis, we have to first define a dead state of the system. The state of the system when it comes into the equilibrium with the environment is called dead state. At dead state, T is representing with the T naught and P is representing with P naught. The properties of system at dead state are indicated by a subscript to 0. The system that is equilibrium with its surroundings has zero exergy and is said to be at the dead state. So at the dead state, the system is at the same temperature and pressure of its surroundings, and it has no kinetic or potential energy relative to its surroundings. So it does not react with the surroundings. Chemically inert. That means there are no unbalanced magnetic, electrical, and surface tension effects between the system and its surroundings. That means mechanical equilibrium. It should be mechanical equilibrium. These are the main assumptions for at the dead state of the system. So exergy forms. There are different exergy forms are there. First one, exergy of the kinetic energy. The system that is in equilibrium with its surroundings has zero exergy and is said to be at the dead state. And also kinetic energy is V square by 2. And next one, exergy of a potential energy. Potential energy is a form of mechanical energy and can be converted directly into the work. Potential energy itself is the work potential or exergy of potential energy dependent of the temperature and pressure of the environment. It represents K X P. P means potential energy, and that is gravitation, universal gravitation due to acceleration due to gravity and elevation z. Exergy transfer by heat transfer. As we add heat to the system, we increase its ability to do work. So it will be represented with the X in the suffix heat is equal to QH. That means heat transfers from the high temperature source into maximum efficiency. That is also Carnot efficiency. So that is equivalent to QH into eta max is the Carnot efficiency, and that is represented with 1 minus T naught by TH. So reversible work and useful work. Reversible work, the maximum amount of work is possible to produce in a process between a given initial and final states. That is reversible work. Useful work, the amount of work done that can be actually be used for something desirable. WU equal to W minus W surrounding, where W is the actual work done, and here some work is used to push the atmospheric air out of the way. That work can't be used for further purpose. There should be loss from the actual work produced by the system. This can be represented as W surrounding, and this is the product of atmospheric pressure P naught into volume difference, final volume minus initial volume. And second, irreversibilities. Irreversibilities I. Except this can be represented with I, or it is also called as exergy destroyed waste work potential. So it represents the energy that could have been converted into the work but was instead wasted. So to have high system efficiency, we want to be as small as possible. So where I equal to W reversible minus W useful for work output device like a turbine, and I equal to work U in minus work reversible in work input device like a pump. So exergy transfer by work. If we do work on a system, we increase its ability to do work. So we can represent it with X suffix work, that is equal to useful work, that is also equivalent to actual work minus W surrounding. This is for boundary work, and X work equal to W for all other kinds of work except boundary work. Exergy of fixed mass. So according to the second law, not all heat can be turned into work. Work potential of the internal energy is less than the value of internal energy. So let us consider first law of thermodynamics, Q equal to delta U plus W, where Q equal T naught into delta S. This is the heat loss from the process. And W useful equal to change in internal energy plus potential energy pressure, that is W useful surrounding minus T naught into S minus S naught. You simply substitute this W as W useful minus W actual minus W surrounding. So and here you substitute that T naught into delta S. After for integrating, this is for a particular state. After integrating, you get this relation, and whereas coming to the exergy, add two more exergy terms along with the kinetic energy along with the potential energy. Exergy of a fixed mass continuum. Here, phi is representing with the exergy of a system at a particular state. So this can be also representing with this. Note that phi is 0 at the dead state. And up to this, I'll end my lecture. Thank you.